back for the course Fluid Mechanics. So in the previous class, we have discussed about the different properties of the fluids. So that is from module 1. So we have discussed the different properties till the viscosity property we have discussed. So today in this class we are going to cover the another property of the fluid, that is surface tension and the measurement of surface tension and the effects of the surface tension property. So that is what we are going to discuss in today's class. So the next property which we are going to discuss is surface tension. First, we'll see what is surface tension. So here it is defined as the tensile forces acting on the surface of the liquid which is in contact with the gas. So that is the surface tension. So which is defined as the tensile forces acting on the surface of the liquid, so which is in contact with the gases. Okay, so here it is also defined as the force acting on the surface between two immiscible liquids such that contact surface behaves like a membrane under tension. Okay, so there are two definitions for the surface tension. We can define it in two ways. The first is, so it is the tensile force. The surface tension is nothing but the tensile force, so which acts on the surface of the liquid. So where whatever the liquid which is in contact with the gases, or it can also defined as the force which is acting on the surface between two immiscible liquids. Okay, two immiscible liquids means, for example, if this is a water and the, so this is water and this is a gas. So between these two liquids, so this is the contact surface. Okay, so on this contact surface, whatever the force which acts on that contact surface, so is called the surface tension. And here, so this surface tension is basically due to cohesion and weak adhesion. Cohesion means it is the force of attraction between the same liquids. So whereas cohesion is the, adhesion is the intermolecular force of attraction between the different molecules. So here, so to occur a surface tension, the presence of surface tension is basically due to a cohesive property. See, the examples for the surface tension is, so here in the pictures you can see the examples for the surface tension property. The first one is, so whatever the needle which is floating on the water. So that is due to the property of surface tension, because see, the needle is a one surface and water is another surface. So between those two surface, so what is, there is a tensile forces. Due to that tensile forces, what happens? So there is a possibility. So it is a chance to float on needle to float on the water. So similarly, so whatever you are seeing, the second picture, the insects, why it can stand on a water, so that is because due to the surface tension property. Similarly, in the third figure, you can see, so the pin can, it doesn't immersed in the water, it just floats on the water. So that is due to the surface tension property. Understood? Surface tension is nothing but it is just a tensile forces. So tensile forces, hope you know what is tensile forces. Okay, so this isn't tensile forces. If you stretch any material, so for example, if we consider this is a material, so you are, I'll just show you here. If this is a material, if you consider, so if you apply the force on the both the surfaces of the material, what happens? The material will elongate. means which is the material is under a tension. So due to that, what happens? The material will bend like this. So that is called the tensile forces. That force will act on this surface, whatever this surface is there, water and this insect, so means the gas. So on this surface, the tensile forces will act. So due to the tensile forces only, the needle, pin can withstand on the water and also insects can stand on the water. Okay, so these three are the examples for the surface tension. So basically, so the surface tension is due to cohesion and weak adhesion. So we'll just continue. So here, what is actually the definition of the surface tension means? So it is the property of the liquid surface to offer resistance against that tension is called surface tension. As the name says, in the name itself you can see surface tension. Okay, so it is the property of a liquid surface to offer resistance against that tension is called surface tension. Understood? So that is the simple definition of the surface tension is it is the property of the liquid surface where that liquid surface, this liquid surface will offer a resistance against the tension is called surface tension. It is denoted by the symbol sigma. Here you can see the symbol which is used to denote the surface tension is sigma, and here the property this surface tension decreases with increase in temperature. If the temperature increases, then what happens? So the space between the molecules, okay, so goes on increases. So for example, if you consider water, if you keep on boiling the water, so what happens? The volume is going to increase, means the space between water molecules, one molecule to another molecule, it is going to goes on increases like this. If the space is more, then what happens? The force of attraction between these two molecules is going to decrease. Okay, so if the force of attraction decreases, then the surface tension will also decrease. Okay, so force of attraction decreases means the cohesion is going to decrease. Cohesion decreases means surface tension decreases. As I said, so it is due to cohesion. Okay, so if temperature increases, cohesion decreases. So that's why the surface tension will also decrease. So in the figure here, you can see what happens. You can see we know the liquid is made up of number of molecules. You can see, so these whatever the round circles you are seeing, so all those are the liquid molecules. We know from one molecule to other molecule, so there will be a force of attraction. Here you can see, so from this to this molecule, and so this to this to this. So between all the liquid molecules, there is a force of attraction between one molecule. So due to that, what happens? The liquid molecule will be under equilibrium. Okay, so this is the top surface. This is the top surface of the liquid. So whatever the molecules which is present below the top surface, so all those molecules, for example, so except this top layer, so all the other molecules below that top surface will be under equilibrium, because so one molecule will attract another molecules. So from all the sides, they, for example, if we consider this one molecule, so then here also there is a water molecule, here also there is a water molecule, here also. So all the molecules will attract each other so that it doesn't move anyway. So it will be under the equilibrium. So whereas if you see the top molecules, I'll show you in a different color. See these top surface molecules, whatever the molecules which is present at the top surface, so above those molecules. Above this top surface molecules, there is no other water molecule to attract, to exist the force of attraction. So that's why what happens, so whatever the molecules which is present below the top surface, these molecules will pull the top surface molecules. Okay, so this second layer molecule will pull the first layer of molecules because there is no molecules at the top. Here at the top surface you cannot see any molecules. That's why, so this second layer molecule will pull the first layer molecules. So due to that what happens, but the between the top layers molecules there is a force of attraction. So due to this downward movement of the water molecules, what happens, so a thin layer is going to form at the top like this. A thin layer is going to form at the top surface. So this surface, this is the tension layer. This layer is nothing but the tension is going to develop at the top surface. Just because this only, so the needle can stand on the water and also the insects can stand on the water. So this is how the surface tension will occur. Hope you understood the concept. So next is how we are going to measure this surface tension. That is nothing but the measurement of surface tension. So here it is measured as the force exerted by a film on a line of unit length. As I told, so here what happens, due to the downward movement of the top water molecules, a thin film is going to form. Okay, so that whatever the force which is exerted on that film on a line of unit length. So it is measured, surface tension is measured as the force exerted by a film on a line of unit length on the surface of the liquid is used to measure the surface tension. So it can also be defined as the force required to maintain unit length of film in equilibrium. For example, here you see the figure here. If you consider this is the object, it may be wire or plate, anything. Okay, and this is a liquid. So here you can see the force. See whatever the force which is, if we consider this as an film, so whatever the force exerted by this film on a unit length on the surface of the liquid. So this is the surface of the liquid. So on this surface of the liquid, so whatever the force exerted by the film on that line only for a unit length, so is used to measure the surface tension. So it is nothing but force required to maintain unit length of film in equilibrium. So that is denoted as sigma is equal to force by length. Simply, in simple terms, we can say surface tension sigma is equal to force divided by length. And here we know the force unit is Newton and length it is meter. So the unit for the surface tension is Newton per meter in SI system, whereas in MK system it is kgf per meter. So kgf means kilogram force per meter. So the surface tension is measured as force per unit length. So it is defined as the force. So from this also you can define the surface tension. It is defined as the force required to maintain unit length of the film in equilibrium. So that is called the surface tension. So the next is, so what are the effects of surface tension? So what is going to happen because of the surface tension? So that is nothing but the effect of surface tension. So we have three cases in that. So which is illustrated, the effect of surface tension is usually illustrated. So by a It is described by three cases, that is water droplet, soap bubble and liquid jet. Okay, so for example, so when a droplet is separated from the surface of the main body. For example, if you consider this is a water, so this is a water. So from this water, so we have taken just a droplet. We have taken just a droplet of water and we have separate. This is the main body. This is the main body. So from this main body, so we have just separated a droplet. So this is a droplet. Okay, so we have separated a droplet from a main water body. And what happens when you separate a liquid droplet from a main water body? So due to this surface tension, what happens? So net inward force causes the surface of the droplet to contract. So obviously in the internal of this inside of this water droplet there will be a pressure, the liquid pressure, inward pressure will exist. So due to the surface tension, that inward force so causes the surface of the droplet to contract. So that's why it keeps the droplet together due to the inward force. Okay, and that force, that internal pressure, whatever this internal force or internal pressure is there, so it is goes on increases within the droplets, within the droplet. So it will go on increases the internal pressure. So as the pressure increases, what happens? The contraction continues. So till where it continues? So till that inward force is equal to the internal pressure. Okay, so this is the inward force. I'll just indicate with a different color. See, due to the surface tension, whatever the red color I am indicating, so that is the inward force. Okay, so due to this inward force only, so the droplet is in contact, it is in contraction due to this inward force. Okay, so that inward force is developed due to the surface tension. So whereas other than this inward forces, there is another internal pressure which I am indicating with the blue color. So this internal pressure will also exist, that is the internal liquid pressure. So until where the contraction of the liquid will occur, so till this internal pressure is equal to inward forces, till the inward force is equal to internal pressure, so this contraction will continue. So once this inward force is equal to internal pressure, then what happens? So the droplet forms into a sphere, so with a minimum surface area. Okay, so the contraction is going to end and it will form a sphere like this and with the minimum surface area. Okay, so is it clear? So first what happens? So once we separate a droplet of liquid from a main water body, or consider consider this is a main water. This is a main water body. From the main water body, if you separate a droplet of liquid, so what happens? Due to the inward force, the water droplet will be under contraction. So due to that surface tension. So other than this inward force, so there is an internal pressure and the contraction is going to continue till where? Till this inward force is equal to the internal pressure. Okay, once the inward force is equal to internal pressure, so what happens? The droplet is converted into sphere with the minimum surface area. And here, so that internal pressure within that liquid jet and soap bubble. So we have three cases. So due to the surface tension, so three cases is going to occur. One is water droplet is going to form, soap bubble and the liquid jet. All the three are due to the surface tension property. So in case of liquid jet and soap bubble, what happens? The internal pressure so increases due to the surface tension. Even in other two cases, so that in case of liquid jet and the soap bubble, so the internal pressure increases due to the surface tension property. So for a water droplet and liquid jet, the internal pressure intensity is more than the outside pressure intensity. So for this droplet and the liquid jet is nothing but a jet of water which is coming through a nozzle with a high velocity. Okay, so for both the cases, so in internal pressure will be more, because jet means it is so with the high pressure, it will be under high velocity. Okay, so for both the cases, the internal pressure will be more compared to the outside pressure. So whereas for a soap bubble, the tensile forces are same in both inside and outside, because so soap bubble both inside and outside the liquid is air. Outside the soap bubble it is air, and inside the soap bubble it is air. So that's why the pressure, the tensile forces will remain same both inside and outside for a soap bubble. So that is internal pressure is same as that of the outside pressure. Okay, so pressure intensity will remain same both inside and outside the soap bubble. So next you have the pressure equation. Pressure equation for a water droplet, for a liquid jet, because the internal pressure for water droplet and liquid jet is more compared to outside pressure. So and in case of soap bubble it remains same. So now we have the three equations. So that is pressure equation for a water droplet, liquid jet and soap bubble. So we'll see one by one. So what is the pressure inside a water droplet or droplet of liquid? So for that you can see the figure. So here, so for that, what we have considered a droplet of liquid. So whatever you are seeing in a figure here, so we have considered a liquid droplet. So where sigma is the surface tension and P is the pressure inside the droplet, that is the intensity of pressure, and D is the diameter of the droplet, and R represents the radius of the droplet. So what we'll do now, so whatever the water droplet we have considered, we'll cut that droplet, we'll divide the droplet into two equal parts. Okay, we'll divide this water droplet into two parts, and now the force acting on one half is due to the pressure inside the droplet on the projected area, and on the other half it is due to surface tension on a circumference. Whatever you are seeing figure B and figure C. See, once you divide this liquid droplet into two parts, on the first part, so whatever the force which is acting, so that is basically due to the internal pressure P on the complete area. So this complete area, the pressure will be acting. Whereas on the other half, the force is due to the surface tension, which will act only on the circumference. Circumference means only on the outer area, outer layer. Okay, sigma will act only on this outer layer, whereas P will act on the entire area, on this exactly on this projected area. So once you divide the droplet into two halves, on first part, on one half of the part, the force will act due to the internal pressure on the projected area, and on the other half the force is due to the sigma surface tension, which will act on the circumference of the droplet. So here we'll consider the equilibrium condition. What is the equilibrium condition? That is internal pressure is equal to outer pressure. Internal pressure is equal to outside pressure. Here you can see the direction P represents the internal pressure, whereas sigma represents the outside pressure. Okay, so for a equilibrium condition, if we take a equilibrium condition, force due to P will be equal to force due to sigma, because inside pressure is equal to outside pressure. That is the equilibrium condition. So internal pressure is due to the intensity of pressure P. So whereas the outside pressure is due to the surface tension sigma. So here, so what is the force due to the intensity of pressure P, which is acting on the complete projected area, is given by P into projected area is pi d square by 4, and so force due to sigma, that is surface tension, is which will act on the circumference. The circumference of the circle is pi into d, so it is sigma into pi into d. Force due to P is P into projected area, that is P into pi d square by 4, and force due to sigma, that is surface tension, is which acts on the circumference is sigma into pi into d. So here pi d will get cancelled. So P is equal to 4 sigma. 4 will go to the right hand side. So you will get P is equal to 4 sigma by D, or in terms of radius it is P is equal to 2 sigma by R. So that is an equation for pressure inside a liquid droplet. So that is P is equal to 4 sigma by D, or P is equal to 2 sigma by D. The next is pressure inside a soap bubble. The second one will see what is the pressure inside the soap bubble, as we have considered the water droplet here also, because you see here we'll consider the bubble. This is a bubble what we have considered to derive what is the pressure inside a soap bubble, and sigma is the surface tension and P is denoted as the pressure inside the bubble. Similarly, D is the diameter of the bubble and R is the radius of the bubble. So as we have done it in case of water droplet, here also will cut the soap bubble into two parts. And in case of soap bubble, the most important thing is, so bubble has a two surfaces which is in contact with air. As you see here, in case of bubble, in case of soap bubble, so both inside and outside, so the surface is in contact with air. So both the inside the soap bubble and outside the soap bubble, air is present. So that's why the surface is in contact with the air both inside and outside. So that's why two surface contributes same amount of tensile forces due to sigma, that is surface tension. As this soap bubble is in contact with air both inside and outside, so both the surfaces contributes the same amount of tensile forces, which is due to the sigma, that is surface tension. So now here what we'll do, so we'll again consider the equilibrium condition, that is internal force is equal to inside force is equal to outside force. So that is inside force is force due to P and outside force is force due to sigma. So inside force which will act on the entire projected area, as you see here in the second figure, internal pressure is due to P, which is P into projected area pi d square by 4, and the force due to sigma, that is surface tension. Here you will get 2 sigma, because inside also air is present, so outside also air is present. So surface tension force will present both inside and outside. So that's why here the force due to sigma, that is surface tension, is 2 sigma into pi into d. So here pi will get cancelled, d will get cancelled. So you will get P is equal to 2 sigma, and here so 4 you send to the right hand side, it will be 4 2s are 8. So you will get pressure inside a soap bubble as P is equal to 8 sigma divided by D. So that is an equation for pressure inside the soap bubble. So the last case is pressure inside the liquid jet. So here we'll consider the liquid jet. You can see in the figure. To derive the pressure equation for a liquid jet, we'll consider the liquid jet of length L and diameter D. So here sigma is the surface tension and P is the pressure inside the soap bubble, and D, R, L are the diameter, length and radius of the liquid jet. So here also we'll cut this liquid jet into two equal parts, and here so one the force which acts on one half is basically due to the internal pressure P, which acts on the projected area, which is nothing but P into dl. So here the area is not pi d square by 4 because it is a cylinder. Means the jet is, you can see jet is looks like a cylinder. So the area of the cylinder is pi into d into l. So force acting on one half of the jet is due to P, which is given by P into D into L. So whereas on the other half, it is due to surface tension, so which acts on the circumference. Here you can see this is the circumference. Circumference of the cylinder is 2 into L. So it is sigma into 2 into L. So we'll consider the equilibrium of condition. So it is internal force is equal to external force. So it is force due to P is equal to force due to sigma. So force due to P is P into D into L, and force due to sigma is sigma into 2 into L. So here you can see the equation, it is P into L into D is equal to sigma into 2 into L. So L will get cancelled. So you will get P is equal to 2 sigma divided by D is the equation for pressure inside a liquid jet. In the next class, we'll just discuss the next property of the fluid. We'll stop here in the today's class, and thank you.